Now we have some basic idea for the application of factorial experiment. Now I want to use a smaller the better case study to present how the application of Takeuchi's method to the real engineering problem. And this is an optimization for replication quality of light guide plate. And this is the topic and the source of the reference. You can check out the detail from the paper. Injection molding, first they melt the resin using heaters in these barrels, and then using the screw to push the melted resin into the cavity of the mold. And then we need to control the pressure, the packing time, and the temperature of the mold. The objective is to minimize the deformation, which might be a shrinkage, warpage of the injection molded part. So the design target here is light guide plate. Light guide plate is a PMMA plate form which has some microfeature on top of it. It is using the liquid crystal displayer to convert the LED light source into a uniform planar light. So the purpose of this injection molding is to produce a plastic part with some microfeatures, and we would like the replication error to be as small as possible. The microfeature we are using here is a V-cut, and this is the size of the V-cut. It is 10 micron wide, and the vertex angle is 90 degrees, so the height will be 5 micron. And it is uniform distributed on a 2 inches light guide plate. And as you can see, the microfeatures of this V-cut is very, very small. So this is very important that we can perfectly replicate the feature geometry on the mold into the plastic part. So here the quality characteristics can be represented by minimize the replication error of the feature height and the feature angle. The ideal height will be 5 micron, and the angle we are talking about is the D angle over here, which is 45 degrees. The control factors, including injection speed and the packing pressures when you push the resin into the mold, and for certain packing time, then you need to hold the temperature of the mold. And for certain time, then you need to cool it down, which is the cooling time. And there's another special technique used in this paper is using induction heating on the mold surface, is to increase the surface temperatures without increase the whole mold temperatures in order to reduce the cycle time. This is the geometry of the mold, and the stamper is setting over here, which is the 2 inches, and the material will be PMMA. So the complete procedure of parameter design will start from define design objective, where we have determined to minimize the replication error. We select the suitable SN ratio, that is a smaller the better case. We have already introduced what is the control factors. Next step, we have 6 3-level control factors. So we need the suitable orthogonal array to put the control factors. The next step, we'll conduct experiment, measure the quality, and determine what is the SN ratios. Then we will use the analysis of mean to find out the relationship between control factors and the output SN ratio to do the parameter design to obtain a design with a maximum SN ratio. And afterward, we need to verify our optimum design in case there's some problems, or in case we would like to further optimize our result. We can change our searching range and iterate the searching process. Here we have 6 3-level control factors. From the previous table, you'll find out that the L18 is the smallest orthogonal array can be used in this design of experiment. Although you can choose a bigger experimental design, such as L27, L36, or L81, but in order to reduce the experimental cost, we prefer to use the smallest orthogonal array, where is L18. If full factorial, the experiment will be 3 to the power of 6, since we have 6 3-level control factors. the total experiment will be 729. And the full factorial is not economically feasible, it's too much. So we use a fractional factorial, L18 in this case, to do the experiment. We would like to use analysis of mean to find out which is the optimum design in the full factorial. Certainly, if you use a bigger orthogonal array, you might have a better accuracy. So this will be a trade-off between accuracy and experimental cost. And in this case, we are using random sampling and to measure the replication quality for the light guide plate. So we arrange our design over here. This is the L18, which contains 1 column for 2 label factors and 7 columns for 3 label factors. Here we only need 6 columns since we only have 6 variables. Because we assume interaction is negligible in this model, we can arrange these 6 factors into any 6 columns of this orthogonal array. We choose column 2 through column 7. And this is the experimental layout. So for each level, we can see the number over here. A has 3 levels, which is the injection speed. You should determine the range based on your engineering knowledge. And the packing pressure is the 3-level packing pressure is listed over here. For packing time and the rest of the factors, the level settings are shown over here. So for the first treatment, you find out that your design will be set at level 1. So you need to find the corresponding value for each control factor in level 1 and substitute into the experimental design and use this experimental setting to find out what is the replication error and then the SN ratio. This is how we do the measurements. We are doing random sample, as I mentioned. In the paper, they select 3 samples from the ejection molding batch. On each sample, they measure 9 locations, 9 points for the replication error of height and the angle. And since this is a smaller the better problems, so we are using smaller the better SN ratio, which is defined here, and delta y is the replication error. So we substitute into the equation, and then we can obtain the SN ratio for each design treatment. And this is the data provided by the paper. As you can see, there are 18 experiments. From each experiment, we are doing 2 measurements. The first one is the replication feature height. The second one is the angle. And this is the average of the total 27 measurements. And this is the corresponding SN ratio for height and for angle. Next step is very similar to our previous numerical example. We are doing analysis of mean. We can use in Excel to assist us to find out what is the response table. Here, as you can see, there are 18, so there will be 6 experiments, which is set at the first level. Same thing for second level and third level. Following the procedure, you can get a response table, and the result is shown over here. The upper part is the error of the V-cut height. The second one is the error of the angle. And this is the control factors, 6 control factors, and this is level 1, 2, and 3. So as you can see, in the first step, we would like to find out what is the parameter design which will give us the maximum SN ratio. By considering only the height, you can see the selection of A1, B1, C1, D2, E2, and F1 will be the best parameters which will give us the maximum SN ratio. However, if you look at the error of angle, find out they are pretty much the same selection except factor E. Since this is a 2 objective optimization problem, now you need to consider whether you want to pick E2 or E3. So you can look at the significance of factor E to the output of height and the angle. As you can see, we need to determine from E2 and E3. This is the effect plot for the feature height. E2 and E3 are not that different. So if you consider the SN ratio of feature height, you might select E2. However, E3 is very similar. the difference is small. But when you look at the effect plot for the feature angle, you will notice that the selection are pretty much the same except factor E. But for factor E, E2 and E3 are very different. E3 is significantly higher than E2. So by balancing the feature height and the feature angle, it turns out that selection E3 might be a wiser choice, since if you select E3, you can improve the ASN ratio of feature angle without decreasing the ASN ratio of feature height. So the optimum design is listed in the paper over here. Since the maximum design may not be one of the designs in the initial L18 experiments, so you need to verify your parameter design. And this is the result showing over here. For the feature height, the SN will be 7.06, and for the angle will be 0.38. You can compare the result with the current L18 samples. You will find out that they provide the maximum SN ratios. And this is the SEM pictures for the optimum design and the initial design. The optimal design can perfectly replicate the V-cut features, and the replication rate for the height will be about 91.6%, and the angle will be 98.1%. Compared with the initial design, as you can see, there's some injection errors. The top of the V-cut is not filled up due to bad selection of the parameters. And in the verification experiment, they injected 50 moles and tried to find out the distribution of the optimum parameter design. And on the top is the initial design, on the bottom is the optimum design. As you can see from here, the optimum design has a smaller distribution, which resulted in a smaller SN ratio and the average loss. The average height of the V-cut will be about 4.6, and the average angle will be about 44 degrees. Compared with the initial design, the height is significantly smaller, which is about 3.0, and the angle will be about 31 degrees. So using this Takeuchi method, we can not only increase the replication rate, but also reduce the variations.